this computer. And we are
All
recording.
right, welcome. So of course, lately, tons of papers have been about models that have been built using transformers. And, it's always interesting if we can kind of learn more about, how they work. So last week, we started talking about this paper. It first came out a year ago, actually, just took us a little while to find it. And the paper is about a model called Rome. And the title is something like Locating and Editing Factual Information in Transformers. So there's a Yannick Kilcher video. We're going to continue watching that. And actually, we're going to back up a little bit. So if you weren't with us last week, I think we're pretty close to the beginning still. So you're good there. And the idea is that they said if you start with a very simple kind of sentence where it's like a subject and at the beginning, an object at the end, and some relationship in the middle. So like the Space Needle is located in, and then you need to say a city, right? Or the capital of France is, and then you need to name a city, right? Abhijit, you mentioned knowledge graphs, so this is exactly that. This is just like simple sentences that are triples. Okay.
Yep.
And so what they did is they took sentences that are like this, where the object is the last word, and they would then run through and they would try and see if they could figure out, well, which weights in this model with millions of weights is causing it to say the Space Needle is in Seattle and not Paris and not Hamburger, whatever, right? So that's in general what this paper is about. And they'll do a better job explaining it than me. One thing that Roger helped us go through last week is that when you see the transformer, there's the original transformer in the Attention is All You Need paper, and GPT and most of the large language models, the generative models today, don't actually use that transformer. They use a slightly modified decoder only. So just going to recap the conversation we had last week quickly. And let me see if I can get this. So I'm going to share my screen. All right, you guys see my screen?
Got it.
All right, good. So the original, Jerry, can you get that? Awesome. All right. So the original transformer you see is this diagram, okay? It's got the encoder on the left, and it's got the decoder on the right. And also it says that you can have multiple layers. That's what this n times means here, okay? But so when you're looking at GPT-3, Chat-GPT, most of these models, this is not actually the architecture that they're using anymore. So in a decoder-only model, these two parts with the big X's are gone. So the encoder's gone, and since the encoder's gone, this little signal that comes from the encoder side to the decoder side doesn't exist. So there's no need to do this cross attention between the encoder info and the decoder info. All right. So if you're used to seeing, again, this full image, really, this is what we're talking about for decoders. And so if we actually snip that out, then this is what the decoder looks like without the encoder. The other thing is that you'll see there's this residual connection. So if you're kind of going up the middle, when you get to the attention, there's a pathway that goes off to the right and it skips around the attention. So just like in CNNs where you have a ResNet, but the way this diagram looks, it's sometimes a little bit hard to notice that. So one way you can think about it is first we can shrink this, and then what we can do is we can just shift things over to make the residual nature really obvious. Okay, so now in this diagram, the pluses mean where signals are getting added together, and you can see very obviously now there's an opportunity for the input, once it's embedded, just to go straight through unmodified, and that whatever's happening in the attention, whatever's happening in the feed forward is just getting summed along with whatever's in this straight path. And so we call this straight path the residual stream. All right, everybody with me? Any questions? Okay,
Good.
so now if we take this, what's really happening when you have a transformer and you have 8 words, 10 words, 500 words tokens, I'm using them interchangeably just for simplicity. Okay, right, you actually have a bunch of them lined up. All right, and so these are just multiple copies of the same thing that we have. And whatever the max length is, 1,000, 2,000, 8,000, whatever. Okay, so now if we shrink this down, then we'll have room to show actually multiple layers. So first, let's just shrink this down. And then now we can add multiple attention layers. And so what you see is that we have attention, feed forward, attention, feed forward, attention, feed forward, and so on. And so if there's 12, 24, 36, 48 layers of attentions, that's now you're talking about this is what like GPT-3 actually looks like. So far we have a diagram that we started with attention, we kept it pretty similar, and we're just saying, hey, this is what Decoder looks like.
Hey, Ted.
Yeah.
Yeah, so one quick comment there isn't a line drawn, but the implication that the attentions, if the right side is the most recent, that attention can attend to all the keys and values to the left of at the same level.
Yes, so like, for example, the token at position 4, when it does attention, it can look at itself, and it can also look at the third, the second, and the first tokens. That's just the way attention works. It's not really shown here, and so actually in a couple slides, you're going to see we're going to add that.
So wait, it can't go to the nth one on the right then in this case?
It can't go to the right.
It can only go to itself and any predecessor.
Yes. So actually, I did not understand this clearly until I was working on just doing this explanation. So I know that when you're on the 10th word, that obviously the 10th word can't attend to the 11th word because it doesn't exist yet. It can only attend to the words 1 through 9, right? But what I didn't realize, I didn't understand, is that even when you're on the 10th word, the 4th word will only attend to words 1 through 3. Words 5, 6, 7, 8, 9, and 10 exist, and it will never attend to its right, the way they've set it up. I actually think that there might be an opportunity to build a smarter model if you let it do that, but it'll be slower to compute, just so you know. It'll be slower to compute, but I think it might be a little bit smarter if you can figure out a way to do that.
You remember that paper I did? They did that in one level, and then they let in the other levels of the vocabulary, they let it attend to everything. So that's interesting.
Yeah. So these decoder only models, basically when you have only the first word, it predicts the second word. And then once you give it the second word, it predicts the third word. What I was reading is they actually don't recalculate all the attention values from the first position, because since it can't attend to the right, there's no need to recalculate it. You only need to calculate like one additional stripe at a time. And then so in training, you can really, really optimize things by parallelizing things. But even at inference time, there are some optimizations apparently that you can make.
And Ted, my understanding is it's that term masked multi-head attention. The masking is that which gives it this causality, only attend to things to the left.
Yeah, it's just I misunderstood. I thought a much looser meaning of masked, meaning that when you're on the 10th token, everything is only looking at the first 10. But actually, it's always the 10 is only looking, and the 5th is only looking at 5 things, and the 3rd is only looking at 3 things, even though stuff now you actually know about it. So it's much stricter than that. Yeah, Ben.
Is the idea that like with the mass multi-head attention that you can create something like a context for each of these following nodes so that it's coherent and remembers, it can have some sense of understanding like what it's talking about still?
So there's two things going on. So the attention in general lets you, yeah, exactly, have that context and understand the rest of the sentence, and you don't have to have some kind of memory, like in an RNN, you have this, hidden signal that's passing, right? You directly have access to every word that previously appeared, and you don't have to, memorize it and code it, whatever. It's right there. Now, of course, you have to have the smarts to pick which word you want to pay attention to. But if you had the smarts to pick it, you have full access to all of its values right there. Okay, so that's in general what attention does. But in a decoder only model, during training, you actually know the full sentence. So if the sentence is 20 words long, you actually know all the words. But when the fourth word is predicting the fifth word, of course, it shouldn't be peeking ahead. So it's only looking at words to its left. At runtime, it actually behaves the exact same way, even when you're on the 19th word trying to predict the 20th word. And I think part of the reason I'm not sure, part of the reason might be that you can't necessarily change things up too dramatically between training and inference, right? So if you always trained it only looking to its left, but then at runtime, you're like, oh, but now since I have 19 words, I'll let you look at those, that might actually screw it up, right? It might not be expecting that, right? That might cause some domain shift for it. So that might be one reason why they don't do it. I don't know, But the other thing is, it is a lot. They can optimize the calculations and take advantage of the fact that they're only looking left, because once say this orange box here has been calculated for the fourth one, even when you add the fifth, sixth, seventh, eighth, ninth, the numbers coming out of this will never change, because it's still only looking at the first three things, and the first three words have never changed. So so there is that, but I don't know. I'm not sure. I think maybe domain shift is more of the issue than just this little performance boost. Okay, so in the paper,
Ted,
yeah, Dave.
So just wanted to, maybe I'm just repeating what you're saying, but just want to understand a little bit better. So what you're saying is, let's say the fifth token was evaluated when it was decoding the previous four for the first time, right? Then when it moves to the 19th token, it continues to reevaluate the fifth token. But when it is doing that, it's attending only to the previous four tokens. It's never looking forward, even when it is trying to reevaluate, when it is evaluating, let's say, the 20th token.
Yes. And so if you do this without any optimizations, you do this in the naive mode, okay? So let's just take, I'm losing my mouse. Let's take this fourth attention and the very first layer, okay? It's going to tend to itself and the first three words, all right? When you're predicting the 19th word, it's still going to be attending to itself and the first three words. So its output is going to be the exact same thing that it output when you were only on the fourth word. Okay, so whether you do the optimization and you cache that and don't actually recalculate it or not, it doesn't matter. Either way, it's going to output the exact same floating point numbers.
So that's important. Yeah. So I think that wasn't clear to me earlier. So even though it's reevaluating, the reevaluation is null actually.
Yeah, and I think some people have figured out a clever way to code it so that it doesn't reevaluate. But even if you don't take advantage of that, it's still just going to keep spitting out the exact same numbers. Okay. Now, what's different is that there's somebody on its right that can utilize those numbers, and they can utilize it in a way that wasn't available to you now. But other than that, you're not actually calculating anything different. So when you're on the 19th word, it's going to go and look at those other 18, things that are sitting out there.
But the only stuff it needs to look at is the cached keys and values from the earlier stacks, the earlier tokens.
That plus it needs the actual data that's on the residual stream to calculate its own 19th key.
Yes, right. On its right. So the earlier tokens, those stacks, you need the keys and values from those feed through the attention into the last stack. And then the only output we care about in that generative way is the last one. That's going to become, you're going to draw from that and create the next token.
Yeah, actually, let me advance to the last slide here. It might be a little bit easier. So what the authors in this paper when you see their diagrams, you're going to see a grid. It's going to look a little bit like this. The difference, however, is that the grid is rotated 90 degrees, okay? The original attention is all you need. It goes bottom up. Most architecture diagrams in deep learning go bottom up, okay? But in this paper, they're going left to right. So what we need to do is we need to actually take this, we need to rotate it 90 degrees. Now it's going left to right, okay? This diagram so far, I haven't changed it. Then what they're talking about is, I could have maybe drawn like dotted lines, but you see there's like an orange and a blue, an orange and a blue, an orange and blue. Each one of those is a layer, okay? And so after each layer, you can think of it as there's a hidden representation there, okay? It doesn't really matter, but technically, like that is true. Like layer 1 is passing its outputs to the inputs of layer 2. So in the paper, they draw these little purple circles to indicate these are the hidden values between each layer. All right. And then finally, what they do is the path along any one token, like this first token, is very clear. Here's the residual path. Here's the residual path for the second token. What's not so clear is that this attention is able to look at things earlier. So now that I've rotated, it's things above it. Okay, so if attention looks at things above it, it means that data is actually flowing downward on this diagram. So what they do in the Rome paper is they add these arrows. You probably can't see the arrows that well, but these orangey lines, they're all pointing downward. So the information from this first token can go to the second, third, fourth, fifth, and onward. The second token can go to the third, fourth, fifth, onward, and so on and so forth. But information from this third token will never go to the first or the second. Even when you're on the 1000th word, and we know this, it still is that the attention is masked in such a way that the second and the first positions will never use information from something that's later in the sequence, which in our diagram is now down. So that means that information in a decoder only, like GPT-3, can only flow to the right or down. It can never go left, and it can never go up. So when they're explaining things, you'll notice that, like, if they show like paths that information flows, it's always to the right or it's always down.
So Ted, just to be clear, this is in the decoder only type mode, right?
That's correct.
Not an encoder decoder, because it's bidirectional then, right?
Yeah. So if you use BERT, which is using encoders, okay, it's not generative. It's not doing next word prediction. It gets the whole sentence at once, and every word looks at every other word.
Okay, because it needs to know the context in which anything lives. So
right. So like if you're using Roberta for sentiment analysis, then every word gets to see the words that are both on its left and its right in terms of figuring out what it means and what the whole sentence means. But in GPT-3, that is not the case. So if you speak with like undefined pronouns, if you say, I don't know if I can, it's not, I don't think it's considered good grammar, but if you just somehow said something like, it was unhappy because the dog was hungry, then technically it has no idea what it means in a GPT style model, because it's the first word. And it doesn't matter, even when you get to the end of the sentence and you've seen the word dog, it still isn't allowed to look at the word dog. It can only look to its left. Whereas in an encoder model like BERT, it would say, I'm going to look both before and after me to figure out. And it would say, oh, okay, it's this weird sentence. It's bad grammar. It's confusing, but okay, I see dog later on, and it might figure out that it must be referring to a dog.
So like
if we use this for Yoda speak, I was just going to
go
say,
ahead,
if we
Grant.
use this,
Yeah, like you like using the sentence use, and I think Roger's saying Yoda speak. Yeah, like I think you can say basically that same sentence, right, Ted? Like because the dog or because it was hungry, the dog ate.
Yeah, and that possibly, if you do a lot of that, you might get slightly poorer performance out of a GPT-3 or a Chat-GPT or something than if you didn't do that Yoda speak, backwards speak, because again, it can only get information from its left. So that's actually one benefit from just studying this, because I didn't realize that. I knew that the last word that you've seen so far, you know, like if you said whatever, because it was hungry, the dog. Okay, I know that it doesn't know the next word. It has to figure out it's ate, you know, but I didn't. I thought that all the other ones could look around by the time you got to dog. But no, it's actually a hard and fast rule that no matter how far you get in the sentence, you still, each position still only sees its limited window.
Hey, Ted, one question on this. Let's say each of these blocks or sub-blocks, let's take a look at the top left, for example, right? That or orangish and bluish block, right? Which is the attention head and the feed
Yes,
forward
so this
network.
is the first layer, first token.
Right. So first layer, first token, though it is, this specific layer is multiple attention heads, potentially, because each layer could have 12 heads or 6 heads. So just to understand that. So all that work that it is doing to produce one token at that point, is that right? So maybe what from the purple circle on the left till it reaches the small purple, that hidden thing that you're showing, right?
Yeah, so the
To
first
the next
circle to
one.
the second one, right?
So that is one token produced.
Yes, so in
First
these
layer.
models, the input size and output size at each token position are always identical. That's what lets you stack as many of them as you want, and nothing ever changes in dimensionality, right?
That's right, but let's say if
So,
this is the starting point, then at the end of first purple circle, we have one token produced, even though the capacity of the inputs is, let's say, 500 500 tokens, right? The input can take 500 tokens or produce 500 tokens, but at the end of first layer, one token is produced. Then as it goes along to the right, and the second input comes in from the second row on the left, right?
let me
So
see.
then,
Hold on a second.
David, I think the first token is not output until the very right-hand side where it says output. So
So you're talking about here, right?
starting point, yeah.
Going to
First,
here.
right. So it's not produced. I understand what you're saying, Roger, but it,
Yeah.
let's assume even if it's reevaluating, it is not changing anything. Let's make that assumption for now, even if it is, but
Right. It doesn't go to the outside world, but it's doing calculations. Yeah, sure.
Right.
So
let's say,
what is your statement or your question?
So at the end of first layer, the first token is produced. Where is the second token produced in this picture?
Are we talking about, we're talking about inference time, right?
Right. When it's a generative model, right? So this decoder only.
Yes. So what happens at inference time is you always generate one word at a time. Okay. So you're going to take however many layers you choose to have. Okay. You could just have the one, but let's just say the way I've drawn it, you've got n layers. Okay. You're gonna only input one word here. It's going to go all the way through, and you're going to make your prediction for what the second word is. Okay. And whatever you predict here, I'm going to put a P here, right? For your second word, you then copy that here as your second word.
So it's kind of sampling from the distribution on that, right?
Yeah. So you do your first sample, and then you say, okay, now I'm going to give you 2 tokens, and I want you to predict the third word. And so then if I pick a different color. Let me see. I'm not too used to using this annotate stuff.
So should there be an arrow, input arrow from where you wrote P2 to where you just wrote 2?
Yeah. So this P2 is copied over here. It's the same thing.
Okay, so there is an arrow which is
So
not shown, but
it's really P.
Yeah.
But we don't think of it as P anymore because once it's been spoken, now it can't change its mind, and it has to stick with that word. Okay.
So the output on the right was a distribution over all the embeddings, right? Word embeddings. And then the one on the left is a sampling of that.
No. Well, okay. It just depends on how you do it. Let's just use the very simple vanilla early version where whichever word has the highest probability, you just say, that's the word I'm going to output. Okay. So you've picked the word and now you just copied that. Okay. So our sentence was whatever, because it was hungry, right? So you started with because, and it said, I think the next word is it. So now you pass in because and it over here. Okay. And now you're going to predict the third word. So we only care about what this prediction of the third word is. What I'm sharing is that technically speaking, if you look over here, the exact same numbers are popping out that passed that happened when you were predicting the second word, because the input is the same here. And all the attention and fully connected layers can only see the exact same things that they saw before. So all this math that happens along the first token position is going to wind up giving you the exact same prediction P2. We don't use it. We don't need it anymore because we've already said what our second word is. But nevertheless, technically speaking, if you run the whole thing again, it's going to output the exact same numbers.
So in other words, you can kind of freeze each layer as you go.
Yes, and so that's apparently, I didn't know this, what some people do is they freeze and cache these values for the attentions that's going to happen later on, because they're never going to change in this sentence. Once you get to a new sentence, then you have to unfreeze everything, right?
Right, you reset.
So then if I
you
change
start
colors and I say that now we're going to do the third word as input here, right? We're going to pass the first word in, and the second word in, and the third word in, and we're going to get our prediction for the fourth word. And to your point about freezing, these numbers that pop out here and here are once again going to be identical than they were in the first two steps.
Yeah, and not just that, even the intermediate connections are all frozen, because
yes, every single one of these numbers
is like taking it from, you know, the previous layer, right, and previous to that, and so on, and so the whole thing is frozen before it.
Yep, everything above your current token position is just frozen, identical. Whether you rerun the calculations or not, you're going to have identical floats everywhere.
But Janeth, I think that they only cache the keys and values coming out of the mass detention. You don't need all the other intermediate stuff.
Technically speaking, you don't need all that stuff. You could just calculate cache the keys and values, because that's what gets used in these orange attention boxes.
Right. Okay. Right.
They don't actually care the purple value. They don't care this brown value, this green value, right? Just the ones you want. But the point is, if you're really clever, you don't actually bother doing this whole calculation again. I don't know exactly how I would program it, but you can just use your imagination. Somebody figured out a clever way to cache it.
So I saw, Ted, I saw in the Hugging Face Transformers library, they just referred to it as a causal transformer, and it's just like an option to the constructor. So they have,
I guess
fairly
causal
common implementation.
If you look at like the vanilla PyTorch decoder, okay, it has a mask that causes everything below your current position to be zeros, okay, and so like the first one can only see itself, the second one can only see the first two, whatever, but it doesn't cache anything. It will actually repeat all the calculations every new token. That's the difference I'm talking about. Is it'll still do this same calculation, but it will actually chew up a lot of flops, right?
Yeah, well, why does it do that? That seems incredibly inefficient by the time you get to the nth token.
In training mode, there's this wonderful optimization. At inference time, how do I say this? The transformer itself doesn't know for sure what you're going to do, right? By the time I've output the fourth prediction, yeah, I could pass those 4 words in next, but I could just decide to change my mind and give you a different batch and give you a completely different sequence, right? You have to be guaranteed that the next batch is going to be the first 3 tokens I saw plus my prediction as the next thing. And if you're just like, you know what I'm saying? If you're just a little PyTorch model, you don't know what the user is going to pass in next. Most likely it's going to pass in, but they could just decide, oh, I'm bored with that sentence. Let me start a new sentence.
Mm-hmm.
So during training then, Ted, it sounds like you can essentially train the distribution for all of the 19 outputs, not just the last one that you're going to use when you're doing inference or generation.
Yes. So what you do when you're training is you go and you pass all 19 in, and you get all technically 19 predictions, 2 through 20 out. And then you calculate losses and gradients on all 19 of those in one fell swoop. So really, it's not that like you've done something super smart and brilliant. It's just you don't bother doing steps 1, 2, 3 through 18. You just go straight to the very last step, 19, because it's going to spit out the exact same numbers as from all the earlier steps. And so in one fell swoop, you get all 19 steps worth of predictions, and you just calculate your gradient off of those.
Yeah, and the difference from inference is that you don't feed in the P2, you feed in the 2 from your training sample.
Yes, when you're in training mode, you give it the ground truth in all token positions as input.
Right.
And then there's another thing in terms of like how you train models. Sometimes even when you do it iteratively, you actually override P2 with the ground truth, because early on, right, if the model's not very well trained, then if it makes terrible predictions, then you start putting these terrible predictions as your inputs, and it's like garbage in, garbage out. It doesn't learn anything. Right?
Sorry, I missed what you said earlier, Ted. I mean, so when do you do that?
No, I'm saying that there's a really good reason for always putting the ground truth as your inputs during training mode.
Right.
Because early on in training, when it hasn't yet learned language and hasn't learned grammar, if you put in its prediction for the second word and it was complete garbage,
right,
then it might have trouble learning, because by the time it got to the fourth word, it's not even a sentence. It's just utter garbage.
Right. I was just pointing out that the difference in the operation. Yeah. The thing too is that it, even though you can feed all the 19, it doesn't look like you can truly parallelize it, because each level uses, each of these horizontal levels or whatever uses the one before it, right? So you kind of have to go in sequence from the top left to the bottom right.
You do have to go one layer at a time. You can't calculate layer 5 for the 19th token until you've calculated layer 4 for all the other tokens. But you can actually calculate 1 through 19 in parallel with each other.
Yeah, you mean the column?
Yes. The way that it's oriented currently, it's column. One layer is now looking like a column.
That is true. Yes. Even there, doesn't like 19 get it from 18, 3 from 2, and so on? It has to flow down, right?
Not during training.
You're just calculating keys and values off of the values. You're not really using that step's attention or whatever, not until you get to the next layer.
Okay.
Jane, in training, the tokens coming in on the left are already known. That's the ground truth. That's the training data. And all you're trying to do is you're going to make the distributions that come out on the right-hand side match the it would be likely for the token in the next column.
Yeah.
Or in this case, next row.
Yeah. So I'm a little confused in the sense that, does that mean that you don't need these arrow connectors during training?
The arrow connectors are not as physical as the other ones. Okay, so you sort of have in memory and you multiply by the key matrix in order to compute a hidden key vector for each of these positions. But you're not sort of physically copying around this data. Whereas for these black lines that go from layer to layer, we in a typical implementation, right, you would just sort of say like, hey, PyTorch, here's my decoder layer, and now I want you to create 24 of them. And so internally, like PyTorch really is, at some point, there is actual like memory, GPU memory that has all of your tokens from layer whatever 5 prior to pushing them as inputs to layer 6.
Mm-hmm.
Whereas for this, it's more conceptual information as opposed to, it may not actually exist. Like these orange arrows that flow that show the attention flow, they may not exist physically in memory. Whereas these purple circles, so this is your question, Dave. These purple circles in most implementations will actually physically exist on the GPU at some point in time. You're going to say, I'm done calculating layer 1, and now I have each of these purple circles sitting in memory. Now I'm going to use those as inputs for layer 2. And when I'm done with my calculations, I'm going to have these third purple circles sitting in GPU memory. And I'm going to use those inputs for the next layer.
And you're saying that, in that, like any of these layers, these purple circles can be computed in parallel. Like if you had 19 GPUs, they could all go and...
Yes, and as currently oriented, the 19 vertically could be computed in parallel using the same inputs.
Mm-hmm. I see. Okay, thanks.
And so whether you had 19 GPUs or you just had like a really giant matrix multiplier or whatever, but like basically you could do this in parallel.
Yeah, one way to think of this, is like the pipeline of the CPU processor. So essentially, new tokens are coming in, even though it shows 1 in the very first top left, the actual capacity of that little pinkish box is 512 tokens. It's just that for computation time flow presentation is saying, well, or Ted is, or in this picture, it's like 1 token is coming in. And the time T2 in the same, if you didn't draw that orange arrow, in the same architecture, the new token is coming in, 2 is coming in, or P2. So, but for showing it as a time series flow, if you may, right? This is how it makes it easier.
Yeah, because we do think of
visualize.
language as a time sequence: first word, second word, third word. Yep.
Yeah.
And Dave, I think it's the dimensionality of the embedding of the token may be 512, but we still consider it 1 token.
No. So you're right. I'm not talking about the dimensionality. So you're right. Token 1 is 512 dimensions, but the input sentence width can also be 512. So it, like, GPT-3, for example, it says when they talk about 2000 tokens, they actually talk about 2000, literally 1000 dimensions inputs.
Right.
Yeah. So great question, Grant. So when we talk about a layer, so let me just pick a different one. Let me pick the 3rd layer here. All right. Even though I've drawn this as 19 positions, every one of these blue boxes is identical. It's just 1 set of feed forward weights. And every one of these 19 orange attention boxes is just 1 set of query key value projection weights. So they're
layer
all
2
doing
is different from layer 3 then, though, right?
Yes.
Okay.
They are physically instantiated as separate. They could, by coincidence, have some common numbers,
Sure.
but yeah, they're separate. So the key thing is that if you had an attention that the query for the word boy and the key for the word he had a really strong match, okay, such that you got almost all the attention, from between those two. No matter where you moved those two words, you would see the exact same strong attention signal. Well, as long as they're allowed to look at each other, okay? We're talking about the whole masking thing, but as long as they're allowed to see each other, you would get the exact same thing, because all of these weights in the orange boxes are identical. They're not different depending on where you are. So, so if you said, because it was hungry, the dog, or you said because it was hungry, the big dog, or you said because whatever, it doesn't matter if you change around the positions, it and dog are going to have the exact same attention score, regardless, because exactly what you asked. This is only one logical set of weights.
Ted, your example though, wouldn't the position embedding be able to affect that attention score?
Sorry. Yes. If the position embeddings come into play, then it can change things, and depending on what it's attending to, if it's attending to only the position, then it wouldn't matter what word it is. It says, I want to attend to the immediately previous word. Fine. Sorry, I was glossing over that a little bit, but it's a good clarification.
Can I ask a question?
Please.
So what defines how many layers of function we have? I feel that this, for each word, this is like a combination of several identical functions. So,
yeah.
But like, what determines like how many layers of function we can have?
Yeah. So in the way we have the picture drawn right now, how many layers is how wide, okay, this diagram looks, and that's really just like the experimenter decides that at the beginning before they start training, and then it has to be fixed at that point.
It's like the depth of the layers, something like that.
Exactly. So if I'm doing a BERT small training, I'll say it's 6. If I'm doing, whatever, a GPT-2 regular, I don't remember what it is. It's 24. If I say I'm doing GPT-2 extra large, it's 36. But you just decide that up front, and then of course, the more layers you have, the more parameters you have, the more weights you have to train, and the slower it takes.
So is this kind of like, because I feel like for this graph, we can basically have all the combinations. So because all the, I think like every node, the words are linked with each other. So I think that is basically we can have like for each word we have the same function of processing, and we can have kind of like all kinds of combinations of the word, kinds of combination of these functions, and to test out which one give us the maximum probability. So that determines the next token.
Yeah, and the one inherent property of doing the dot product attention the way we do is that if you don't look at the positional information, okay, then if the weights are trained to do something like find the verb or match the word dog with the word it, those rules automatically will work no matter where the words are, whether they're 2 words apart, 5 words apart, or 10 words apart. Okay, that's one of the fundamental challenges that we had with RNN LSTM type models, is that the farther the words got apart, the harder it was to remember and have that hidden signal, maintain all of the information. So what we trade off in the transformer, because you can directly see all the other token positions, okay, you have no cost for words being farther apart. What you do have is you have more computation cost.
Yeah, it seems like we have to at least have a matrix of this size of like this map.
So basically when you read it, but what people talk about is that there's a quadratic cost, so that if you have 1,000 length sequence and everyone is looking at every other one, you have 1,000 squared comparisons of different token positions. Okay. If you have 1,000th length RNN, it's still only doing 1,000 calculations one at a time.
Because it's linear.
Because it's linear. Okay.
Yeah, that's true.
There's some, you can have more complex LSTMs or whatever, but it's in the ballpark linear cost. Okay. But in the attention, you have this quadratic cost, which is why it works better, but you generally haven't seen even experimental transformers with sequence length longer than 8,000 typically. There's a few exceptions, but like 8,000 is 64 million compares. And so going beyond that, it just gets really slow to train it.
Thank you, Ted.
Yeah, thanks for the question.
Hey, Ted.
So you don't actually need 19 GPUs, to Ranjit's question in the chat.
Yeah,
So basically, when you pass in a sentence during training mode, and the sentence is 19 tokens long, you pass in all 19 of them at once. And what you will see is that you will get the prediction for what the second word would be if you only knew the first word. And you will get what the prediction for the third word is if you only knew the first two words. And you'll get what the prediction for the fourth word would be if you only knew the first three. You will get every single prediction as if it only knew that much, because the mask that they apply when they do the calc, I'm like pointing at my screen, you can't see, but the mask they apply zeroes out for like the second token position, it zeroes out everything from the third position on. And for the 12th position, it zeroes out everything from the 13th position on. And so that mask looks different for each token position, and it's done precisely to zero out all the things that you're not supposed to peek at. And so it does that calculation in parallel, and you get, by just passing in all 19 tokens once, you get all 19 predictions, second word through 20th word, and then you can back propagate loss off of every one of those predictions. So even though you really only did one forward pass, you're getting 19 losses instead of one loss that you can. And then if your token size if your sequence length is 1,024 in training, you could theoretically concatenate a bunch of sentences until you got close to 1,000. And so then you're getting the benefit of like 1,000 losses at once that you can then do gradients on, and you don't have to iterate one word at a time to get 1,000 losses.
So in this picture, right, it means token 1 is being calculated 19 times in parallel.
It's not. It's that it will give you the same numbers no matter how many times you ran it through. So you don't need to do it 19 times. You can do it once, and it's the same as all the other 18 times.
Yeah, I mean, yeah, that's the point I'm confused at, because I mean, I feel like if this is being calculated 19 times, even though it's identical, I can understand why this is done in parallel. But if it's not being calculated 19 times, we only do this calculation once.
Yeah.
Then how come this is happening in parallel?
Right. So this is a clever trick, by the way. It's not critical that you understand this clever trick in order to understand how transformers work. Okay. But basically what happens is, what I was trying to show is, if you only passed the first token in and you just had the green data here, you're going to get certain numbers that pop out at the end. If you pass the first two tokens brown in, okay, then you're going to get a new prediction here, and you're going to get the exact same numbers that you got here. If you pass the first three with red, each time you do this, you're going to get the exact same numbers. So why should I bother doing any of the first passes? I'll just do the very last one when I have all 19 tokens. So it's not really parallelizing as much as saying you only need to do it once, and you'll get all the predictions, and then you calculate losses on all the positions and back prop. Did that work any better or no?
It's almost like
You know,
I'm still confused with the parallelization.
Yeah.
So can I take a quick shot?
Please,
Um,
please, yes.
So one clarification is there's a difference between training and when you're doing generative. In the case of generative, you would feed it just token 1. You would run a full forward pass to generate this probability distribution P2. You would sample from that to get your second token. This is in generative mode. To get token 2, you would then have to feed token 1 and 2 all the way through to generate P2 and P3, but you wouldn't use P2. You'd just sample from P3 to generate the third token. Then you'd run that again all the way through. So Ranjit, yes, in the generative mode, we'd run it through 19 times. In the naive mode, you would actually run all, the first token would run through 19 times, second token 18 times, etc. The optimization is they realized, wait, we don't need to run one through that many, don't need to run it through 19 times. We can run it once, cache the keys and values, and then we can, when we're generating 2, the P3 and P4, etc., you can just use the cached values. So that's during the generative mode. When you're in the training mode, you already know what the 1 through 19 tokens are. So you do one forward pass through all the layers to generate P2 through P20, and then your loss function is the difference between P2 and the actual ground truth token 2.
So Roger, so in this picture, right? So if you convert this into a grid, let's say a matrix. So let's say in the training phase, you have P1 through P19, right? And you're doing a forward pass. And if you look at 1, 1, let's say it's a cell, right? So that guy still requires information from token 1, right? From second layer. Second layer, second token would still require information from second layer first token, right? During forward pass or no?
Can you say that one more time? I'm not sure.
So let me see. Okay, I can control the screen.
Token 1, yeah, token 1, layer 1.
Yeah, token 1, layer 1 is fine. Now token 2, layer 2, right? During training phase, when we're doing forward pass, don't we need the information from second layer token 1?
Right, which is exactly why when we say it's running in parallel, you ran the first layer on all 19 tokens during training. So you have all of the outputs from the first layer. And therefore, that's why token 2, layer 2 can attend to the previous layer. So it's actually the part that you're attending to is generated in the mask attention. It will generate the keys and values inside of that. By the time you get up to where you're attending to it, you generate the keys and values and queries. Then you multiply all those against all the tokens at that layer.
So if I could jump in, Ranjit, for your specific question, absolutely, the token 2 does need to know about token 1. And in fact, when you get to the very end, the 19th token needs information from all the 18 tokens that came before it. That's not the important question to ask, however. Did it need all the information from other tokens that came before it? The question is, in the process of calculating the result for the 19th token, did I accidentally also calculate just about everything needed for the 18th token prediction? And the answer is yes. You accidentally calculated virtually everything you needed. And you calculated virtually everything you needed for the 17th, 16th, all the way through the prediction that comes out of the first position. So it's not that like something magical happened, you didn't, whatever. It's just that the later calculations are so repetitive of the earlier calculations that if you just do the last one, you've now like kind of got everything. I don't know if that helps.
I understand the freezing part. There's no need to calculate like the top row over and over again 19 times, right? So I totally get that. What I'm not able to see is the parallelization where, so here's another, maybe this one last attempt. So if you take the top top leftmost purple box purple.
Okay, let
circle.
me pick a color here.
You have the green arrow going to it. Yeah, that one. Yeah, and then you go to the one below it for the second token. So the question is, do you need to calculate the first purple circle before you can calculate the second?
You do not, but you do need to calculate this output
Yeah, yeah.
before you can do. You need to run all the first layer stuff through before you can do the second layer
That
stuff.
that I see. That I see. But going down, you don't need it, right? Yeah. Okay. Thank you.
Potentially all the layers.
Not to, sorry, just wanted to say not to take people's time away, but I did point to a picture where, see, the only reason why it seems a little confusing, and I know, Ted, you have done this to explain the Rome diagram, which makes total sense. Oh, sorry, your highlights are also coming on top, and that may screw up the other thing. But if
I can erase them, but if I do that, then they're gone.
I'll let people answer that, but maybe they can just focus on this diagram because the orange color of decoder block is pretty clear. So if you focus only on the right part, which is the decoder block, so you see at the bottom Y0, Y1, and so on and so forth are the inputs, which is what Ted, when he rotated the picture by 90 degrees, it becomes his P0 or P1, P2, P3, right? And on the top, when you see I1 is going back into the same architecture, right? It's the same decoder stack, if you may. So the reason for us, the reason he broke it down in those top to down layers, but first turning it 90 degrees and breaking it down is to explain the Rome flow. But the actual flow is the same set of units, if you may, hardware units, if you want to call it, or the logical decoder blocks. When you're training, you already know what is going in. Forget the encoder part. Let's say you're just doing the decoder autoregressive part training, right? So you already know boss, it, will, in, or whatever it says there. I think it's the translation that's happening there. But whatever it is, right? So you already know your ground truth. You're sending all of it, and on the other end, I1, I2, I3, all will come out in one go. And the only thing it has to do that in order to train for I1, it knows its position 1. So it should not worry about anything before because there's nothing before. In order to train for output I2, it already knows that the previous words are boss and itch. So it should only train that part while it can send it all in one go. So that's how the training can, I don't know if it has the answer, but this was just one more attempt to help.
Yeah, I mean, that explains the freezing part, but the parallelization is a little bit different.
All right, let me say something different, okay? So whether we do training or inference, what we do is we get inputs and we run it through the decoder block here for all positions that are presently available that we care about, okay? And once we've calculated all, let's say 19 of these, then we do the second decoder layer, all positions that are currently available, whether it's 1, 19, 1,000, whatever, we do all of those, okay? And then depending on how tall our thing is, if our thing is 12, then when we get to the 12th one, by the time we're then we get our output heads and we're gonna get actual predictions, okay? That's the way the calculation works, regardless of whether you're doing training or inference. And I don't think it's actually really that, I mean, I'm happy to explain it. I don't think it's really all that important to understand, like, okay, fine, there's this nifty trick that people speed this thing up. But like, what you really just need to understand is that if you've got all of these inputs, Bach, it, will, ein, Otto, Kaufen, that the attention blocks, depending on the way the masking works, is going to look at other words all at once in this one decoder block. So this one way on the right here, Kaufen, is going to also look at Otto, ein, will, and ich. It's going to be able to look at all of those and decide what it wants to compute for its attention and calculations and whatnot. That's the important thing to understand. Okay, so in a decoder, things only look to the left, but you're calculating this whole block in parallel. And then you started with these words, and now you're going to get some intermediate representation that's no longer those words. It's been modified by this first layer. And then the second layer knows how to work with that modified input. And it's going to look at all 19 positions, and it's going to do its calculations and predict its attentions, and so on and so forth. And so with relatively few, because I think, you know, they started out with like, with whatever, you know, BERT being like 12 layers or something like that, and a small was only 6. 6 is not a lot of layers to sort of, you know, transform a sentence into, you know, really meaningful embeddings for each word. So I don't know if that helps. Again, that's not answering the parallel question, but that's just like what's happening and what you absolutely need to know is happening.
I think I got it. I think.
Yeah, Ranjit, think of it as the CPU pipeline, actually.
Yeah.
Yeah. Just one other thing, and I don't want to belabor, just I'll add this, and sorry, I'll not say anything after this. Maybe I'll not just say it. You go ahead. It's okay.
Well, at this point, I don't know what to do. Roger, you're still on, I think, by phone, but so it's 7:40. I don't think I can even really start the video with 15 minutes left.
Yeah,
I mean, I think this was
I think
valuable.
we slide into.
I think that, you know, the way you've laid this out is fantastic. Thank you for that.
I agree. I concur with that.
Yeah, I would definitely
This is
agree too.
amazing, and yeah, thank you really for that.
Yeah, I agree.
All right. So
Ted, I think you're right. What maybe we just call this the review, the architecture review, and just push the video off to next week.
Yeah.
I think it was useful for everybody to go through this.
So let me just say that there is one last slide. So this is what the picture looks like in the actual Rome paper. So you guys okay if I erase the annotations? I mean, I think I can save them, but
just if they want it, you know, we can always pull it out of the video or something like that. So
oh, that's true. Okay, the recording. All right. So I'm going to clear all my drawings. All right. So if I go back and forth between these two, one mistake I made is you'll notice that my attentions and feed forwards are above the residual path. And in their diagram, they're actually below instead of above. Okay. So that these two diagrams are not exactly equivalent because of that. But otherwise, the purple circles represent each layer of transformers. So this is the first layer. Whoops, don't do that. This is the first layer here. The square is attention, the diamond is the fully connected layer. And then this is the second, the third. So they're showing 3.5 layers and then a final layer at the end, okay? So let's see here. These blue trapezoids are what's taking the words and turning them into, you know, embeddings. And that's this pink box on the original transformer diagram. And then I think they have an output thing here. Here it's shown as whatever, some kind of gray or blue, green, whatever, the linear and the softmax. And they show it as a trapezoid here. And they actually don't bother showing you all the earlier ones, because when you're doing predictions, when you're not training, when you're doing predictions, you only care about the last one anyway. So they just omitted the facts. Physically they exist, but you're ignoring them. And so if you have, again, one of those subject, relationship, object sentences, the Big Bang Theory premieres on, name a TV network, CBS. So ultimately what they're doing in the paper is they're trying to say, can I wiggle the numbers in this network to try and figure out how I can get the output to change from CBS to some garbage? And then can I wiggle them back in a way to restore the word CBS? That's a purposefully poor description of what they did, because I don't want to try to explain the exact process. But ultimately, they're only using sentences of this form, subject, verb, object, that are basically knowledge graph triples. And so then the paper itself is about, they figured out a way to actually do this. And then they saw some really interesting patterns that nobody necessarily knew would be the patterns. And finally, what they did is they said, okay, I think that CBS, that the Big Bang Theory is on CBS is stored in this particular, in this particular set of feed forward weights inside this green diamond right here, okay? And to prove it, what I'm going to do is I'm going to edit some of these numbers, and I'm going to get my transformer by only editing those numbers in that one box there to change it from CBS to HBO. And they were able to do that. And they say, and if I change the number slightly differently, I can get it to say Showtime. And if I change it a little bit different, I can get it to say NBC. So that was how they proved, like, not only do I think it's there, but just by wiggling some of the weights, I can make it say whatever I want it to say.
Hey,
Just
Ted.
for triple relationships.
So when they change that, does it change the network name, or it outputs some garbage sometimes?
I mean,
so my question,
again?
my question is, like, by this time, based on all of the knowledge that's there in various other floating points floating around, or tokens, changing that changes the name of the network, or it changes the word to some garbage? So it's like right now the examples you gave were like from CBS to HBO, or from CBS to whatever, right? But can it be, well, the Big Bang Theory premieres on Paris? Like,
yeah, actually, they probably could get it to say anything they want. I mean, they were the examples in the paper were always semantically similar, right? So
and
so
then
ultimately,
when they, sorry to interject, and when they changed it, did they change it with a specific new set of tokens, or they just randomly changed it?
no, they decided what they wanted the new output to be, and they forced the change that they wanted. Okay, and so they actually measured like sensitivity and specificity. So, for example, they would say, "All right, now I'm going to change the wording in the sentence. Instead of the Big Bang Theory premieres on, they changed it to my favorite TV show, Big Bang Theory, is on." Or whatever, you know what I'm saying? They mixed it up. And what they found was that it had like 99.9%, sensitivity, in that all of the different variations of the sentence would correctly change from CBS to HBO. It wasn't only if you worded it exactly the same way as the first sentence. So then they're like, yeah, so that's a good sensitivity. That shows that it really is associated with Big Bang Theory, because I can change the sentence around and it'll do it. Then what they did is they said, now let's put in a bunch of TV shows that are on CBS that aren't Big Bang Theory. And some of the previous papers that had tried to do edits that would corrupt those other ones. So in terms of specificity, now some other show would change from CBS to HBO, even though it shouldn't. Okay. But in this case, they showed they have very good specificity. It was not perfect. It wasn't, 99.99%. But for the most part, when they made that edit, other shows would stay on in their appropriate things. And so that was what they, so like basically if you changed the Space Needle is located in Seattle to get it to output the Space Needle is located in Rome, that would not be impressive if every single other building, it now just said Rome no matter what. The Empire State Building's in Rome, you know what I mean? And blah, blah, blah. The Astrodome is in Rome, right? That the Golden Gate Bridge is in Rome. That would not be very impressive, but they had both good sensitivity and specificity.
So is it possible to have multiple solutions to this? Meaning, instead of changing one location, change some other location and get the same sort of answer?
We'll see in the paper next week that actually there's multiple layers like near each other where they made the change, and sometimes like the token above, below a little bit. So there's some fuzziness to the location, but I mean, So I'll just say, so basically what they found was the last token of the subject is usually the prime spot. So in this case, it would be theory. So token 4 and in the middle layers is where they found this information seemed to be stored, was in the middle layers. So they didn't say this, but I'm just going to say high level, it looks like the earlier layers are just figuring out how to parse sentences and understand things. And then the middle layers seem to be retrieving facts about subjects. And then the final layer, depending on what the sentence is, you could be asking what network is it on? You could be asking what day is the show? You could be asking who's the star of the show? So it has to pick which fact of the many facts it knows about Big Bang Theory to output. And so the later layers are tending to the whole sentence to try and say, what does this sentence really mean? What's the important information I need? And then if you ask it what network it's on, then it's going to pull out CBS. If you ask it what day of the week it's on, it's going to say, I don't know, Thursday, whatever.
So basically, Ted, you're saying what makes that triple stand as a fact is what they're isolating. That particular triple, the subject, the object, and the relationship.
Yeah. So ultimately, again, we should read the paper and they'll probably say it better than me. Ultimately, what they're saying is that the later layers really understand sentences and what are you asking for. The facts appear to be in the middle layers.
Right.
And specifically, they did ablations where they look to see, is it in the attention or is it in the feed forward? And it's in the feed forward. So, and this is not how they said it, but the way I'm characterizing it is that sort of all the facts we know about Big Bang Theory are getting dumped onto the residual stream into, remember the residual stream, it's like 1024 floats, right? So you can have CBS in a few of them, you can have TV show in a few of them, you can have the star is, I don't know the name of the actor, in a few of them, and you just have all of these things sitting on the residual stream, and then the later layers are the ones that actually decide what to output.
Right.
So that's the super short TLDR for what the paper covers. And so the title of the paper is like locating and editing facts, but actually I think in some ways what's more interesting, I don't know, it's super interesting the fact that they found where facts are stored, but that they found out how, like in general, how and where facts are stored versus sentence parsing happens is almost as interesting as the fact that they could find specifically, you know, what city the Space Needle is in.
New levels
in a small set of weights.
Yeah, new levels of interpretability. Really,
yeah.
Breaking that.
Yeah. So that was what really caught my eye. Although the editing part is still pretty awesome, but
yeah. To me, it's just interesting that there is just a group of locations or a subset of these that store that fact. You know what I mean? That it's not diffuse throughout the entire model. So
yeah,
Right.
it'd be pretty neat if they figure out how to examine all the beliefs of a model. List them all.
I don't know if it lists them all, but I think the paper does a pretty good job of going through a lot of pieces parts. If I remember just my quick scan of it.
So this diagram here is the gist. So basically in this middle region, they're pulling all the facts about the subject, and later on they show only from the feed forward networks. And then down here they show only from the attention networks. Is it trying to decide you know, what information to extract? So they have these diagrams that look like this. And so they're saying they've narrowed it down to not exactly one single place, but a fairly small region of all the possible attention units and feed forward units, and then a relatively small-ish set. And this was a pretty deep thing. This looks like this is like some 48 layer, pretty big GPT-3 model or something.
Yeah, this sounds almost like human neural mapping. You know, over here is where you taste things, and over here is where you you know,
exactly,
you know, spatially, you know, your spatial orientation lives, or whatever you want to call it.
I think the paper talked about, like, neuroscientists talk about like the grandma neuron, that you might have like one neuron that if they zapped it, then like you would forget your grandmother, you know. So it wasn't quite that localized, but basically, you know, they were able to, with 99% success, say, I'm going to make edits to just a single MLP. And that will change it from Seattle to Rome, or it'll change it from CBS to, you know, Showtime, or it'll change whatever.
Does that mean there's a way to hack a one of these transformers?
Yeah. They said in at the end in the whatever that ethics statement section, whatever, right?
Yeah.
They say,
Don't
hey,
do
like
this,
this
yeah.
might help with interpretability, but just beware. It means that bad guys might be able to hack your model if they ever got access to it.
Yeah. So if you were doing something like, you know, is this valid or not valid? You know, you could kind of go in and tweak some parameters, maybe. So interesting.
Yeah.
Fascinating.
Right. Are we about finished then, Ted? Do you have anything more?
No,
Hey.
I mean, we were supposed to watch the video, but I guess that'll be for next week.
Hey Ted, while you were describing, I was cross-checking everything you were saying against Chat-GPT. I'm just kidding.
Oh, you had your audio interface feeding it to Chat-GPT, right?
If it disagrees, then I'm probably right, and it was probably hallucinating.
You could say that now, Ted, but in about 6 months, you're not going to be able to say
Oh
that.
my God. Probably not even 6 months, you know.
Yeah,
do you
it's
know,
learning
like,
exponentially.
yeah, like Stable Diffusion, it came out last year, maybe May, June, July, I don't know when it was. And they just came out with a new version, which is 30 times faster. It's generating an image every 0.1 second or something now. Oh my gosh. So like you can generate a 0.01 second, so you can generate 100 images a second.
Yeah, but has it figured out that you only have 5 fingers on your hand?
It will. It will.
Actually, I do think that part's gotten better too.
Okay.
Yeah,
because it had that problem before, right?
Yeah, that was the very first version, Jerry. I know it's hard to keep trying the newer versions. They're coming out so fast.
My little brain, I don't have the capacity to deal with multiple versions of those models at the same time. So,
You know, we need an AI to test the AI models, AI robot or something.
yeah, we're all going to be obsolete pretty soon.
All right, so I just put a link in the chat to the slides that I was showing, the little transformer diagrammy stuff. So if anybody wants to grab a copy
Hey,
of that.
Ted, great
you.
slice and great effort. Thank you so much.
Yeah, nice job, Ted.
Thanks.
All right.
Yeah, that helped a lot.
I'm going to stop the recording now. People can continue if they want.